Okay, so what we're going to do is before we start getting into the coordination chemistry theory, let's talk a little bit about coordination chemistry. So when we talk about transition metal coordination chemistry, the example that first got gained interest had to do with this. If you look at a number of solids, you find that there's a solid of cobalt-3 chloride, and the color is orange for this solid. And it turns out that when you react this with silver nitrate, in a solution, what we see is that there are 3 moles of chloride, okay, for every cobalt-3 chloride in an ammonia solution. However, when we do the same thing with cobalt-3 chloride, however, we find that we have 5 ammonias associated with it. The color is different. This is a purple solution. And when you react it with your silver nitrate, we find that we have 2 moles of free chloride available. We can also do this. We have 4 ammonias associated with it. And we have 2 different colors. We have one solution that can be green and one with the original formula where it's violet. Okay, so you have the same formulas, but they are different color. And when we react it with silver nitrate, only 1 mole of free chloride can be determined with these different formulas. Now, the original formulas, though, all of them have cobalt-3 chloride in them. So what is happening that we see these differences? So instead of actually writing our formulas in this fashion, which doesn't really describe the differences that we're seeing, we have what we call a coordination sphere formulation. So what does a coordination sphere formulation look like? And why would we want to do this? So for the first one, it has 3 free chlorides when you react it with silver nitrate. What we do is we write down our coordination sphere. And it turns out that the cobalt forms a cation. This is my cation. And this is my anion, like in any salt formulation. But what we're saying now is that my cobalt is bound to 6 ammonia ligands, and I have 3 free chlorides to counterbalance it. So if we draw this, the nitrogen on the ammonia is bound to the cobalt. The ammonias are now called ligands. So I have a cation, which looks like this complex right here, with a positive 3 charge. So my anions, I need 3 chlorides to make my whole ionic compound neutral. This also means then, if I reacted the previous one with silver nitrate, I only found 2 free chlorides, then what does that look like? If I write my coordination sphere, formulation, we have my cobalt, but instead of 6 ammonias, I have 5, so I also have a chloride in there. I have 2 chlorides here. This would be my cation. Okay. And if I draw my coordination sphere, I would have 5 of my ammonias, which we call ligands, bound to my cobalt, and I have 1 chloride bound to the cobalt. So now instead of a 3 plus, it's a 2 plus, and now I have my 2 chlorides so that my total ionic compound is neutral. This is my cation. These are my anions. Okay. So what about the last one? Let me see if I can just. So if I do my last one, we have my cobalt. Let's get this up. Okay. Got my cobalt. Again, cobalt 3 with 3 chlorides. In this case, with 4 ammonias. And I have a green and a violet version. So why would I have 2 different versions? Or 2 different colors, 2 different properties? So again, if I draw my cobalt, and when we reacted with silver nitrate, remember we only had 1 free chloride. So that must mean that 2 of the chlorides are bound to my cobalt. And the remaining positions will be with the ammonias. Since the chloride is a -1, it's a plus, I have a free chloride. So now let's take a look at an alternative way of drawing this. Suppose I had my cobalt again, but instead, suppose I put my chlorides here. Okay. Oh, I have too many chlorides. Hold on 1 moment. There we go. Notice that my chlorides same side here. They're next to each other. Whereas here, the chlorides are opposite. Okay. On opposite sides. So what we find here is that the orientation in space of where my chlorides are located are in different places. And because of that, we have what we call geometric isomers. With their opposite sides of my planes of the cobalt, this is trans. And they're on the same side as in this situation. This is called cis. So when we write down our formulation, it would be trans, and then we write down our complex. And then we write down my anion. So this is my cation. And the chloride's my anion. And we can do the same then for my cis complex. So we say cis, write down the formulation of my complex. This is my cation. And this is my anion. And that's how we have, let's go back to our physical properties. That's how we have, even though we have the same formulas that we say, oh, it's cobalt 3 chloride, but in actuality, with the complexes, we can see that these are all distinctly different compounds. And that's what we're interested in studying. So what we're going to do is go through the coordination chemistry and discuss Werner's theory in greater detail.